In the previous lessons, we learned how to draw Lewis dot structure from a chemical formula. And we also learned how to interpret the Lewis dot structure in terms of the chemical bonds and the lone pair. Now, we are going to look at the Lewis dot structure and determine the chemical properties of that molecules. Especially, we are looking at the polarity of a molecules. First of all, before we talk about polarity, we need to realize that polarity is based on the electronegativity of an atoms, or the atoms in the molecules. And basically, how it works is that if we define electronegativity, it is the ability of an atom in a molecules, okay? Keep that in mind. It is in a molecules, and this atom, or this particular atom, is participate in a chemical bond. So it is bonding with another atom, and we know that there are single bond, double bond, and triple bond as well, okay? Because in a chemical bond, of course, those electrons are now shared, and each atom will have its own ability to attract those electrons. But the problem is this, that different atoms have different abilities to attract electron, and we define that by electronegativity. And let's review. These are the number that represent the electronegativity, and we know that fluorine is the most electronegative. If we look at the periodic trend on the periodic table, going across, electronegativity increase, and going down, electronegativity decrease. Okay, so just paraphrase this on your notes. You can just draw this like this. Okay, going across, En increase, and going down, En decrease. You don't have to draw the whole entire periodic table, okay? And the general pattern is that the smaller an atoms going across a period, it is more electronegative, okay? And we can prove that right there. Going across, the atomic size actually gets smaller. And it makes sense, because a nucleus in the middle of an atom, or in the center of an atom, and this is a small nucleus, so the electron's right here. But if you have a larger atom, where the nearby electron is right here, it will be a lot farther than the one right here. But electronegativities is not just limited to how atoms attract electrons, but it's also define the type of bond. Well, first of all, what we're going to do is we're going to look at the electronegativity differences. The greater the differences, the greater the attraction of electron by a particular atoms. And if we notice, when you have the difference between 1.7 to 4.0, we have ionic bonding. And what happened in ionic bonding, the electron is completely transferred to another atom. So this is where we have loss and gain of electrons. Then we have between 0.1 and 1.6, we have something called a polar covalent bond. And if we have the difference between 0 and 0.3, we have something called a nonpolar covalent bond. So covalent bond have two types of bond. One is polar and the other one is nonpolar. That takes us back to the term polarity. And polarity, basically, the uneven distribution of shared electron, that's because they have different abilities in terms of attracting the electron. Remember, that is a shared electron in the chemical bond. This is in a chemical bonds, okay? And we are referring to single bond, double bond, or triple bond. Okay, keep that in mind. That difference in terms of ability create a dipole moment. That moment, think of the prefix di. What is di? That is equal to 2. So basically it has two polarity. One is what? Positive. The other one is going to be negative. And we're going to talk about that later. So remember, the prefix di means 2. Okay? Two ends. Okay? And the is more polar when it has a greater dipole moment. So the greater the differences of those two ends, the greater the molecules in terms of polarity. And all we have to do is look at the electronegativity differences of the 2 atom. Not just 3, but just that 2 atom, because 2 atom is the one that involved in a chemical bonds. So even we look at this molecule, it has 3 atoms, but when we look at the bond, it's happening between just 2 atoms. That is the chemical bond right there, okay? So that is the definition of polarity or a polar covalent bond. And in a covalent bond where it's nonpolar, the electronegativity of one atom is almost equivalent or equal to the electronegativity of another atom. Therefore, there is no uneven distribution of shared electron. Now let's look at how do we determine the polarity of a molecule. So of course we are going to look at the difference of electronegativity between 2 atoms that are bonded together, okay? Then after that, if we have more than 2 atoms involved in this molecules, we're going to look at the overall shape or the symmetry of the entire molecules. Well, symmetrical molecules tend to be nonpolar, and we're going to look at that in a moment. And asymmetrical molecules tend to be polar. And of course, we're going to look at that in a particular minute. Here I have the Lewis dot structure for water. Of course, I ignore the lone pair right here. And when I generate to the 3D version, notice, look what happened. If you look carefully, right, we have a negative charge right here, and a positive charge, and a positive charge. Well, of course, if we look at this right here, that is hydrogen is 2.2, and look at oxygen is 3.4. Which one has greater strength in terms of pulling the electron? Of course, oxygen, 3.4 versus 2.2, and that's the reason why if we look at this molecules, the oxygen has a greater strength in terms of pulling the electron. And if you are pulling the electron toward you, of course you have a negative charge, and where the hydrogen, it would not have the electron most of the time, and that's why it has a positive charge. And this is represented by this simple delta. Let me write out the word delta for you. That is delta symbol right there. And delta basically represents the partial charges that's occurring because of the difference in terms of electronegativity. In this case, we have a positive delta for the hydrogen, but on the oxygen, we would have a delta negative, okay? Now let's look at this molecule where we only have 2 atoms. And if we look at chlorine, right, look at chlorine. Chlorine is 3.2 and hydrogen again is 2.2. What's the difference? Of course, chlorine is a lot larger in terms of strength, so that's the reason why this molecule, when we generate a 3D structure, this is the molecules, this is the polarity direction of HCl. And of course, this will have a delta negative because all the electron will be pulling by the chlorine atom, and this will be delta positive. So far, we look at molecules that are polar. Let's look at a molecule that is nonpolar. So first of all, we have CH right here. That's the bond right there, right? So look at CH. C is carbon, which is 2.6, and hydrogen is 2.2. Notice that is extremely small in terms of their differences, and that's the reason why this is considered nonpolar. NP represents nonpolar. And this right here, the 3D structure shows us that it has almost no charges at all, because their differences is so small. So it's pretty easy when you have a simple compound where it's only 2 atoms, or the differences in terms of electronegativity is small. We can easily identify if it's polar or nonpolar. But what about when we have more complicated molecules that has a lot of atoms in it? And there's a lot of bond that's involved. Now we have to look at the overall shape of the molecules. We have carbon bonded to 4 different chlorine, right? And when I take the Lewis dot structure and I generate the 3D model, look what we have. See, if you notice, this molecule is actually nonpolar. It doesn't have any arrow going one direction. And look at the symmetry of these molecules. Notice we have chlorine is a lot more electronegative carbon than carbon, because right here chlorine is 3.2 where carbon is just 2.6, right? So of course the electron is going to be going that direction, going that direction, and going that direction. But what happens when you have this direction pulling that way and that direction pulling that way? It actually cancels it out. The same thing in this case, right? That direction pulling up, this direction pulling down, it actually cancel out each other. And that's where the symmetry involved. Because of its symmetrical shape, the force of this direction is canceling out with the opposite force. And then, if we look at this one right here, we have carbon dioxide, which is the gas that we breathe out. And of course, we know that if we look at the oxygen, it is 3.4, where carbon is just 2.6. And of course, we gonna draw the arrow going that way and the arrow going that way because it's the same strength, right? If I'm pulling that way and another guy pulling this way, is this carbon gonna go anywhere? No, it's actually cancel each other out like this. This cancel out equals to 0. And that's why this is nonpolar. Where if I change this molecule to another compound, where I take this oxygen and replace it with sulfur, look what happened. So let's look what happened. Sulfur, it is what? Sulfur is 2.6, the same thing as carbon, where oxygen is what? 3.4. So if we look at this very carefully, this is 2.6, this is 2.6, and this is 3.4. Of course, it's going to have a dipole moment of going that way. But is it going to be a lot? No. It's going to be very small. Okay, and this makes this compound polar. Let's look at another example. Notice how this compound is very similar to that compound. The only difference is that the shape-wise is pretty much the same in terms of Lewis dot structure. Notice how we have that 4 atoms around a central carbon. But if we generate a 3D structure, this chlorine is extremely negative, we just mentioned before, compared to carbon and hydrogen. So that's the reason why it's going to have a net dipole moment toward the chlorine, giving itself a partial delta negative, and this would be almost 0, because the difference between carbon and hydrogen is very little. And this shape, even though on the Lewis dot structure it looked very symmetrical, but by just having one different atoms, it is now asymmetrical. So therefore, this is actually a polar molecule. The same thing happened in this case, right? This is very similar to that, except I take out one of the chlorine and replace it with a bromine. And look what happened. Now you see a bunch of arrow. Look at the green. They kind of cancel each other out. Okay, so this one cancels each other out. But the bromine and the chlorine, this is asymmetrical. See, this is asymmetrical because no longer is evenly pulling one direction in the opposite direction as well. So this makes this molecule a polar molecule. Okay. Now let's try a more complicated molecule where we have a lot more atoms involved. For example, here we have chlorine and carbon and hydrogen, right? And we notice, of course, the chlorine is more electronegative. It's going to point toward that way. And we can guess right away, look at the Lewis dot structure. We're going to have a dipole moment of going toward that direction, which I generated through this structure, but it just flipped the other way. Okay? So that's very easy to see that this is asymmetrical. Even though it is symmetrical this way, but the overall symmetry, because it's going toward this one direction, the force is not symmetrical in a way, right? It's going toward one direction, so therefore it's making the molecule polar. Now, what if I take this same molecule and I put the chlorine on top here? So this is now the direction of the electron on that end, the top end, and the bottom end is actually going in the opposite direction. So in this sense, the force of that direction and the force of that direction doesn't look like this. Look what happened. Of course, it's canceled out. And it turned out this molecule is nonpolar. So be careful. You have to build the molecules to be familiar with how a Lewis dot structure will give you if a compound is polar or nonpolar. So let's do an example. We're going to draw the Lewis dot structure for these molecules. And then we're going to convert to 3D molecules using the MoView.org. So of course the Lewis dot structure for this is very simple. We have oxygen in the middle, hydrogen. Of course, notice how I evenly space them out because I know electrons repel each other. And then of course I have 2 lone pair. I know this already, okay? And then I'm going to build this using the mobile.or. So I take my single bond and generate the atom, and there are 3 atoms involved, and I change the molecule to hydrogen, right? I click on it, and I change the central atom to oxygen, and that's basically my hydronium ion, which is H3O+, and I convert it to 3D. And notice how this does not give us anything, but you can actually go and choose a specific model, the J molecules, okay? And look what happened when I press the 3D. It's a lot larger than before, right? And with the J model, now we have a different feature to look at. You go J view, you can actually look at the charges. And all you do is click, convert to 3D again. Notice how you have the charges right here of all the atoms in this molecule. We have the negative charge, which we predicted because oxygen is very electronegative. And most importantly, we can actually look at the overall dipole of the molecules. So you can see that it's going toward the oxygen, okay? So let's go back and fill out the information. Of course, particular molecule consists of how many atoms? Of course, 4 atoms, 3 hydrogen and 1 oxygen. And its oxygen atoms has how many single bond? We look at oxygen, it has 3 single bond. How many lone pair? 1 lone pair. And the overall polarity of this molecule, when we talk about polarity, either it's going to be polar or nonpolar. So in this case, it has those polarity arrows. Those are called the dipole moment, okay? So in this case, it is going to be polar. And if it's polar, does the compound have a dipole moment? Yes. So once you know this answer, you also know that answer as well. Now let's do another example where we look at possible the opposite of what we have on top. So we have oxygen right here, right? And I know oxygen, each one of those is 6 electrons, but there are 2 of them, so 6 give us 12 electrons. Those are valence electrons. So we have oxygen and oxygen. There is no central atom. And first we draw the single bond, and we just use 2, so we minus 2 give us 10 left. Now we've put electron around an atom, so they are octet. So this one has 2 already, so it's going to need 6 more. But we use 6, so we have how many left? We only have 4 left. So we're going to put the 4 remaining one over here. And if you look at this atoms over here, this atom only has a total of 6 electrons. 2 from the single bond and 4 from the lone pair. So of course we need to make a shared pair of electrons. We call that bonding. And I'm going to borrow this, and I'm going to bring it right there and make a double bond, if that's enough. If it's not, then we share some more. And of course, we have enough. 2, 4, 6, 8. And that is our structure for oxygen. So let's go build these molecules. I can, of course, trash this. And I know that it is a double bond. And I'm going to change that to oxygen. And I'm going to change that to oxygen. So let's generate a 3D structure. And if you notice, does it have any arrow at all? Those dipole arrows are not here, right? That's because there are no difference in terms of their electronegativity. And of course, now we can answer this question very easily. The molecule consists of 2 atoms, and one of its oxygen atom has 1 double bond. And how many lone pair? 2 lone pair. The overall polarity of this molecule is nonpolar. And does it have a dipole moment? Of course, no. If it's nonpolar, it will not have a dipole moment at all. And in later lessons, we are going to look at how polarity of the molecules can be used to determine how it's going to interact with another substance.